Newton's three laws of motion exercise. Newton has three laws. Law 1, object just stay the way it goes. Law 2, acceleration will depend on the force. Law 3, which has a separate meaning, which means when there's action, there's always an equal and opposite reaction. Conceptual questions exercise. Number 1, a passenger is sitting in the rear of a bus and claims that she was injured as the driver slamming on the brake, causing the briefcase flying towards her from the front of the bus. But if you were the judge in this case, what disposition would you make? And please explain. Well, this is exactly the case that Newton's first law will apply. And the bus and the person and the luggage and all goes in the same velocity, forward. So forward in the same direction. But when there's a brake and the slam, but that is only on the bus. So the bus slows down. Based on the first law, if there's no external force, everything continue going forward. So the luggage will go, this is the luggage, forward. So the judge says we'll dismiss the case because he knows from Newton's first law, the luggage will continue going forward instead of going backward, flying toward the city and injure the lady. So, well, case dismissed. Now the second question, 4.2. A space explorer is moving towards the space far from moving through the space from planet or star, or it is in the space. Usually they give us our impression that everything in the space is so light, floating. That's just because of no gravity. But the Newton's second law is still at work. Just because everything is like drifting around, looks like very light, looks like air balloons, but Newton's second law applies, which means if the mass is large and still takes large force to accelerate. So mathematically, Newton's second law goes like this. Acceleration is proportional to the force and inversely proportional to the mass. So if the mass is large and then you take a stronger force, if you kick it, it will require force, it will hurt your foot. So, which means the answer is gently push. Just look like that thing is drifting around doesn't mean it's kind of a light, easy to kick, easy to move because it has a large mass. So that's simply Newton's second law applies. All right, Newton's second law, Newton's three laws of motion continues. Question 4.11. Identify the action and reaction pairs in the following situations. I worked out the first one. I'll let you do the second one. So this is about Newton's third law of motion. When there is action, there is an equal and opposite reaction. So then it always go in pairs. Now, so say this is the person. So his 1 foot is front and he pushes the ground. So that's the ground. So he's going to try to move forward, of course. But then there will be a force. So there should be a force and foot to ground, okay, which is a vector, okay, and there's also a force ground, also push the foot, it's also a vector. So then obviously based on your daily experience, the ground pushing the foot and the foot at the same time pushing a ground, and there are two forces acting on two separate objects. They are equal in magnitude and opposite in directions. Obviously you know that you're going to push the ground backwards, so the backwards you're going to do backwards, while the ground will push you forward. In fact, so that foot to ground that way, and ground foot this way. In fact, it is this foot, the ground foot, this one moves the man forward or accelerate forward. So you have sort of a counterintuitive why the ground is not moving, it can move the man forward. That's Newton's second law says. Well, the force of the ground is pushing the man forward, but the ground for the person is ground to the person is forward, and the person to the ground is backwards. Well, the other two questions, a snowball hit a girl in the back, or a baseball player catches a ball and a gust of wind strikes the window, and I let you figure it out and draw these pairs. Which one is forward, which one is backward, or upwards, downward, and so on. Now let's move on to the next question. Draw the free body diagram for each of the following situations. A projectile in motion that in the presence of air resistance. All right, a projectile in motion in resistance of so free body diagram is you assume an object is totally free and first, and then count every force that acting upon it. So that's called a free body diagram. First, let's consider a projectile in motion in presence of air. So first of all, anything that moving in the air or even fluid will experience a resistance called a resisting force, and that force is always in the opposite direction of where the object is moving, or in other words, is in the opposite direction of the velocity vector. Once again, the resistance force is always in the opposite direction of velocity vector. Usually it is somehow proportional to the velocity, but always in the opposite direction of the velocity. In other words, if you are in the wind, or in the air, you move forward, and the air resistance will be backwards. If you are sideways, and then the air resistance will be in the opposite direction. So always in the direction of the motion. So that's the nature of air resistance. And if you look at the free body diagram for the projectile, and then of course everything will experience on Earth a gravity, which is mass times acceleration, g. So there are two forces. So this is free body diagram. If you draw it over here, free body is free. There is a gravity, mass times g, and there's air resistance. So the resistance that way. So that's the free body diagram. So why do we want free body diagram? So we want added vectors on this free body, and then that total resultant vector will dictate where the object will be accelerated, in which direction the object will accelerate. Now, the second question, the rocket case. A rocket leaving the rocket pad and its engine operating. So, and like the free projectiles, but then there is air resistance, but as I said, it's in the direction, so resistance force is downward. So there's a vector going downward. So resistance, well, I'll draw is down. So rocket, the velocity is going up. So the resistance is down. And of course, it has a gravity down. So both going down, m times g. But then in addition to these two, the rocket's engine is operating. How the rocket engine operating? It pushes some hot air substance up downwards. It's like pushing this thing downwards. Okay, so exhaust from the rear. And then the reaction force is upward. So this pair, the rocket pushes air down, and the air reaction force pushes the rocket up. That's Newton's third law. So there's another force called the throttle force, pushing it up very strongly. So T, I will note with T. So there are three. So resistance force and gravity is down, and then the throttle force become from the reaction force of the air and up. So this throttle force overcomes both the resistance and the gravity, so the rocket overall will go up, or accelerating upwards. Okay, and the third question, an athlete is running along a horizontal track, and that question they leave to you to draw a free body diagram. If I draw the rocket free body diagram is this, let me draw it with little space. The rocket, so gravity and resistance, and then throttle force is this big. So this one from the engine will overcome these two. So accelerating is going up. All right. The heaviest invertebrate is a giant squid, which is estimated to have the weight of about 2 tons, spreading over its length of 70 feet. What is its weight and in newtons? So this question actually lets you know the difference between the weight and the mass. So the weight is actually the gravity force on an object. Since the gravity force is simply proportional to the mass, and in fact it is mass times g, and so the weight and mass is sometimes confused between each other because it's just a g different multiplied with g. So on Earth, especially on Earth, so people use the weight and the mass interchangeably, but not, in fact it's two different concepts. Now, mass of this squid is actually 2 tons. And this is 2,000 kilograms. All right, so the weight is actually mg, which is gravitational force. So mass times acceleration, it is mass 2,000 times gravitational acceleration is 9.8 meter per second squared. I sort of omitted the units. It's 1900 and 600 newtons. So that is the weight in newtons. So that's the solution. To have a more explanation is normally you will call it gravitational force on a 2-ton object. Or you can say it's a gravity force on a 2-ton object, but which is 19.6 19,600 newtons. And sometimes you misunderstand the 2-ton force. That's actually a misconcept, but it's convenient, you know. So that's actually 2-ton force is actually means 19,600 meters. So then what in reality what is happening is the Earth, it attracts the object, the squid in this case, with 19,600 newtons. So you can call it a 2-ton force, or you can call it 19,600 newtons, but the mass is MASS is always 2,000. But if you are to take the mass to the Mars, it will have a different weight, but the mass is the same. But if you take the mass to the Moon, because the acceleration is much less, you have much less weight, much less than 19,000 newtons, but the mass is still the same. So next question, 2.2. A football pounder accelerated a football from rest to 10 meters per second during this time in which its toe in contact with the ball, and 0.2 seconds. With this, you can calculate what is actually the acceleration. So from rest to 10 meters per second. And then the next question is, if the football has a mass of 0.5 kilogram, what is its force? What average force does the pounder exert on the ball? So they actually require 2 steps to solve this problem. First, if you want to know the force, right, you must know the mass, which is known, but acceleration. So mass times acceleration, that's the force. But you don't know the acceleration yet. First, you have to calculate the acceleration. So the acceleration is actually equal to the change in velocity and change in time. So velocity change is from rest to 10 meters per second. So that's 10 minus 0, which means rest. And the time is 0.2. So that gives you 50 meters per second squared. All right, so now we got the acceleration. Then we have the mass, which is 0.2 kilograms. So 0.5 kilogram times 50 meters per second. So it's 25 newtons. So that is the force. Here are 2 more questions on Newton's second law application. 4.2.3. 6 kilogram object undergoes an acceleration of 0.2 meters per second. A. What is the magnitude of the resultant force acting on it? So normally just write down the Newton's second law. So that part A. So the acceleration, once again, in proportion to the force. The more force, you have more acceleration, and inversely proportional to the mass. So now we know the acceleration and we know the mass. So what is the force? Then of course you can see in many posters, mass, if ma, you simply multiply the mass to the other side and you get this formula. In this case, you will have 6 kilograms times 2 meters per second squared, and then you will get 12 newtons. So there's 12 newtons. Now another question, if the same force applied to 4 kilogram object, what is the acceleration? Well, B, if the same force, which is 12 newtons, applied on the same object, so the same force, okay, and so now same force, now it's 12. But this time mass is different, it's 4 kilograms. So say 12 newtons, 4 kilograms, well, it's less, same force but less mass. Obviously it was lighter, and that would be 12 divided by 4, you will get 3 meters per second squared. So compared to 2, and you have 3. So more acceleration, of course, less mass, more acceleration. Makes sense. Now, next question, 4.2.17. A force of 30 newtons is applied in the positive x direction to the block of mass 8 kilograms at rest on a frictionless surface. This question is combined with dynamics and the kinematics. which is we learned last semester. And then first we find out the acceleration, and then second part of the question is how fast it is going after, how far it is going after 6 seconds. So A, acceleration is easy. It's nothing but A and force divided by the mass. So 30 newtons and 8 kilograms, and that gives you 3.75. Well, you do the math yourself. So with the acceleration and second part of the question, B, how fast it is going after 6 seconds. So now recall what we learned the kinematics in the last semester. The velocity as a function of time is nothing but v times t plus the initial velocity. In this case, the initial velocity is 0 and simply v times t. So simply v times t, and this time is 3.75 times 6 and equals 22.5. 22.5, that's meters per second, which means after 6 seconds, since it's accelerating at this rate, the object will reach 22.5 meters per second. So that's the question. Now, if I ask you additional questions, so C, you may get this question: how far, the distance, how far it goes at t equals 6 seconds. So how far it goes, because it's accelerating, then they will require another formula, which is C, which is the added question, and then there will be the distance, which x is one direction, right? And it's equal to half of a t squared, that's the acceleration part. And plus, if it is already initially going, it is initial velocity times t plus the initial location. But in this case, and that is 0 because there is no initial velocity, and that is 0 as well. So only thing left is half a t squared, and that gives you half acceleration 3.75 times 6, this is the time, seconds, and that, if you go through the math, it will give you 67.5. 7.5. So how far it goes is 65 meters, and what is speed? 25.5 meters per second. What is acceleration? The force divided by the mass, 3.75. Okay, this question involving vector addition, but it's still in the neighborhood of Newton's second law and free body object. 4 forces acting on an object given by A, B, C, and D. They are in north, east, west, and south. And what is the magnitude of the net force on the object? What is the direction of the force? This is actually a math problem. Okay, if you want to solve this physics problem, you must know how to solve this math problem, namely the vector addition. Okay, let me use the scale. Okay, I would say 1 millimeter on paper is equivalent to 10 newtons. So the first force on the object is A. Okay, and I must draw, so it's 40, and I must draw 4 millimeter long to the east. So to the east is this way, 4 millimeter long. So B is 50 newtons, but it's to the north, but 50 newton will be 5 millimeter long, and C is to the west. Well, 70 is stronger, so it was 7 millimeter long. Okay, and I will put a colon here, and D is to the south, 90 meter long, 90 newtons, so it's longer. So D. So there are 4 forces. The 4 forces are on the object. If you just visualize it, free body diagram, A goes that way, okay, and B goes up, and C goes to the west, okay, and that's C, and D goes down 90. So to determine which way this object is moving, we need to add these 4 force vectors and get the resultant vector, and then that dictates where they're going. So, and to add vectors, whichever 2 add together and add everything together, the order really doesn't matter. As long as you add them all together, and they will be good. So now let's see. See, now since A and C are along the same direction, so that's A, we add them first, okay, and C is this way, so they are canceling each other, but not totally canceled out. So of course, the whole thing, the resultant is in favor of C, so A plus C, which is this way, is in the west, right? It's in the west. And how much is this? So this is 40, and that is 70 to the negative x direction. So you end up with a 30 to the west. So it's 30 to the west. So that's A plus C. Now, B and D are in the same direction. So B is up 50. And D goes down 90. So they are in the same direction, so they cancel out. So B is 50 and D is 90. So of course D is stronger, so the answer is B plus D give you a 40 this way. Very little, but it cancels out. 40. So B plus D is 40. So you will have this one and plus this one. And overall, you will have, we want the total resultant, A plus D plus C plus D, but we change the order, is nothing but same thing as A plus C plus B plus D, because we can easily do it by hand. Now, so what that is, so the whole thing, the total, the resultant is a force. Let me enlarge it, okay, not follow the scale. 30, so that's the result from A and C, and then 40, the result of the B and D. So what is the magnitude? Since it's 90 degrees, so the magnitude, so we learned from last semester, is the square root of negative 30, that's x component, and square root of negative 40 under the square root. And then if you work through the mass, it is 900 plus 1600, and if you take a square root, and you'll get 50 watt, 50 newtons. So that's the 50 newtons this way. So that's the resultant force. You add them. So that's the resultant force. That's the magnitude, 50 newtons. And what is the direction of the force? So that's A. So the answer A is here. So just recall we did this in a little bit smart way. Is like we add A and C first because they are on the same line. They cancel out. and then B and D second, and then together, and then you have a 40 and 30. So that's this. So 50. Now, what is the direction? So direction angle, if you recall, it is nothing but the arctangent, the inverse tangent of dy over vx. So in this particular case, it is negative 40 over negative 30. So if you use the calculator, you will get 53 degrees. But realizing that this arctangent is multi-valued, so 50 degree is this. So now the direction. So this section I work on direction. So direction, So then if you have that, so arctangent you have 57 degree. So 50. So a arctangent or inverse tangent is multi-valued, which means they have all other, it's possible to have other value for this angle, but the calculator only give you one value within the upper, the first two quadrant. But then it's up to us to determine what actual direction is. In other words, in our case, if you add 100 degree to here, our resultant force is in this direction. So it's adding 180 degrees, so the total is 233 degrees in here. So that is the answer. So that 230 degree. So that's the direction. So to summarize, that's the answer. Let me see if I can change the color. So that's the magnitude, and this is the direction. So just summarize again. So we need to add the 4 vectors on the same object. So we can add any two as long as we add everything, finalize it, and we'll get the same result. But for convenience, we add A and C first. So because they are on the same line, they cancel out, become 30 newtons to the west. And then we add B and D, so it becomes 40 newtons to the south. And then down here we are adding this. Down here we add this one here again. So 40, 30 and 40, and we get a 50. So the final result, 50 newtons to, well, southwest, 50 newtons southwest, and the direction is 233 degrees this way. So I added one more question outside of the textbook, 4.4.7 extra. In above question, if the object has mass of 10 kilograms, what is the magnitude and direction of this acceleration? Well, acceleration, the direction is simple, it's the same as the force. So if we have worked out the resultant force, so above 4 force, let's imagine the same object is here. There are 4 forces, so it has 10 kilograms. This 4 over rho is equivalent to one single one going in this direction. Going to this direction. So it's like 50, we got it from Bravo, and at 233 degrees, 33 degrees. So the whole point is that you work out the free body, you get all the force, and the only thing you need is the resultant force. So 250 resultant force. Then you will know what is the direction. Well, direction is 230. It's going this way. So the magnitude and the direction is 233 degrees that way. So 230 degrees, 33 degrees, and the magnitude. And the magnitude is the acceleration, right? So acceleration, again, is the force divided by the mass. So the force is 50 newtons. The mass now is given 10 kg. So it is 5. So it is 5 meters per second squared. So that's easy. So that's the whole philosophy of Newton's law and dynamics. First, if you have a free body object and figure out all the forces on the object, and then you have a vector addition problem, and after that you have a force total. So then the answer here is you have a force from above, but in this case the acceleration is in this direction, and that is the acceleration. So that ends this chapter. You will get more questions, but it's similar to all the above questions. Hope this is helpful. Have a great weekend.